Oh, our last talk will be given by Sandvik from Boston University.
Okay, thank you. Good afternoon, and thanks to HOQE and the other organizers for having me here. It's my first time in Houston, in fact. So today I will talk about single-hole dynamics at the deconfined critical point. And the deconfined critical point is this point that separates an antiferromagnet and a spontaneously dimerized, valence bond solid in an antiferromagnet. And today I will talk about mainly what happens when you inject a hole into these host states. So this work is done primarily with Sabine Young, who's here in the audience, and also with some help with a couple of former students, Bowen Zhao and Gabe Schum. And also, since I need to give some introduction before I start injecting any holes here, I will also discuss, what we believe about this phase transition and this deconfined critical point, if it even exists, with some results from this paper here. Okay, so a quick outline. Okay, so we'll describe what is deconfined criticality. So it's basically this transition, as I already mentioned. And then I will talk about models in which we can study these states and this transition using numerical methods, primarily quantum Monte Carlo simulations. So these are what we call designer models because they're not supposed to contain the details of any specific material, but they are more used to study phenomena more broadly. Okay, so it turns out that this transition is actually weakly first order, but it's so near by a critical point, likely this so-called deconfined critical point, that we can still regard it as critical in terms of extracting exponents and things like that. So we'll give a quick review of that. And also the fact that there's also other calculations that we sort of agree with when we calculate exponents and things like that. There's also a higher symmetry emerging at the critical point. Okay, so then I will turn to dynamics and first just tell you about some past work on the dynamic spin structure factor, which is something that could be mentioned with neutron scattering, for example, in elastic neutron scattering, if we had a suitable material to show this phenomenon. And then I will switch to the recent work, which is on the single particle, single hole spectral function, which is what you would measure in ARPES, for example. And there, the main question is there spin charge separation at this critical point? Now, there's actually a potential experimental candidate for deconfined criticality. So if time permits, I will actually just with one slide show you some experiments on this material. But there are no ARPES work as far as I know so far. Okay, so deconfined criticality, I think the concept was introduced in this paper by Sentil et al. Already 20 years ago. Although they relied on many past works on how the Nell order can be lost and you can transition into another state in a quantum magnet on the square lattice. So basically you start with the Heisenberg model on the 2D square lattice, and then you add some other interactions which preserve all the same symmetries but destroy the Nell order. And then the question is what happens? So this is the illustration of the Nell state, which of course breaks O3 symmetry. And in this is the theory of what happens when you go into a spontaneously dimerized state, where you can think of these as singlets. Okay, so this breaks Z4 symmetry. There are four different patterns like that, and one of them is chosen. Okay. But then there's actually an emergent symmetry of this state as well. Okay, so the specialty here is that this transition is supposedly generically continuous instead of what you would expect within Landau theory when you break two unrelated symmetries, you would expect the first order transition. So this calculation that was done in this paper was basically elevating the symmetry of the spins to SUN, and then they did large N calculations, and that showed this generic continuous transition. But then it's of course not clear what happens if you go to small n, in particular to n equals 2. Now there were later theoretical work as well as numerical work as well, which actually indicated that it's even more interesting than what they suggested initially here, namely that these two order parameters would actually combine into an SO5 order parameter. So we would have, 3 components of the Nell order and 2 components of the VBS order. It's a 2-dimensional order parameter, and that would combine into an order parameter with 5 components. Okay, so I should point out that this was the scenario of a generic quantum critical point, but you can always assume that, let's say that this is the generic critical point here if you tune some parameter g, but if you also tune some other parameter which doesn't change the symmetry, that could end at some special multi-critical point. And then it would be a first order transition after that. So that had not been discussed so much. It was basically, the theory talked about this generic transition here. All right. Okay, so how about numerics, which I'm involved in? So we want some models that have these two ground states, obviously. And it turns out that we can basically cook up something that works. So basically, the Heisenberg model you can think of as singlet projectors on nearest neighbor sites, right? So now to correlate singlets and maybe get this columnar valence bond solid state, we can actually take products of singlet projectors as shown here. And that actually, when these interactions are strong enough, we will actually destroy the Nell order and get into this columnar valence bond solid state. Okay, so there's been a lot of work on these and related models, and we do have a phase transition here, and there's also signs of this higher symmetry, but it's still not quite clear what really deconfined criticality even is in terms of what actually happens. So basically, if you have a critical point, you can ask, what are the relevant perturbations of the critical point, and how many are there? So in the original scenario, which is more or less illustrated here, there was supposed to be one relevant direction, the one that corresponds to changing from the AFM to the VBS, like here. So there would be one line where you can go on the line and basically nothing changes. But numerically, it always looked like we have some weak first order nature of this transition. So that could mean that we are actually, when we tune a single parameter in our model, for example, in these JQ models, that we are actually on on the first order side here, but pretty close to this continuous line of transitions. Okay, but then something else could also happen, and I think that's actually more likely. Namely that there is actually no such line at all. Instead, there's a spin liquid phase that opens when you cross that point. So there's a critical point there, but no line of generic critical points. Okay, so then it turns out that if we look at these models where we combine J and Q2 or J and Q3, then we actually get very close to these critical points. Well, one of these, whichever scenario applies. Whereas if we take, for example, the J and Q6, then the transition is very strongly first order. So we can see that we sit somewhere here. Yeah, please.
Is the endpoint the same universality class as a line, or is it some kind of...
Well, that we actually don't know. At least it seems like if this scenario holds, they must be different. It's like a tricritical point, it should be different, right? That's right.
Should that think about that like a deconfined critical point or something?
Yeah, so that's even a question. Should we even call it a deconfined critical point then, right? So, we do, because there is some aspects of deconfinement there, which is what I hope I will get to, right? So let me just quickly show you some numerical results that show that we have this transition and that it's actually very weakly first order. So we can look at what's called bin accumulants of order parameters, which have this nice property that, if you have an ordered phase, the corresponding bin accumulant is 1 if the system size is big enough, and in the other phase it's 0. So you see here, as a function of J over Q, you see that we start to develop these step-like functions. And if we look at the AFM cumulant and the VBS cumulant, the steps are opposite, and they seem to happen at the same point. So, for a long time, we actually believed that the transition is continuous here, because if we look at long distance correlation functions, like here we look at finite lattices and we take the longest distance on the finite lattice, these correlation functions look like as a function of the inverse of the size or the inverse of the distance. The correlations seem to decay with some power law to 0. So if you just look at this, especially if you don't have the biggest sizes, you would say, okay, look, it looks like it's critical. But if we really blow up the scale here, so this is both spin and the dimer here, and here I separate the spin and dimer, and here I take 3 nearby couplings. You see that actually they extrapolate to some very small but non-zero value. So that actually means that these order parameters coexist, but they are very small at the transition point. So in that sense, the system is near critical. Okay, and it turns out that if we compute, scaling dimensions or critical exponents, if you will, we get results that are actually very close to other calculations. For example, there's this so-called bootstrap, conformal bootstrap method, which just, puts in a symmetry, and they're supposed to get everything from that based on conformal field theory. And also there's this so-called fuzzy sphere approach that Inch and Herb invented a few years ago. And without going into what these scaling dimensions are, I just want to show you that they look rather similar. So I think now it's fair to say that, okay, whatever the ultimate nature is of this critical point, these models that we study are sufficiently close to that critical point to study it and analyze it as a critical point. So the next step then, after we have looked at critical exponents and things like that, we can start to see what's the nature of the excitations. And these we can probe again with spectral functions that you could in principle access experimentally, like the static spin structure factor, not the static, the dynamic spin structure factor, and the single hole spectral function. So, yeah. So again, okay, good question. So I don't want to get into it here because it would take a long time to explain all the nuances of this, but basically you cannot completely trust any of them. And in fact, the bootstrap method actually needs an input value in this case. It takes one numerical value as input, namely the one with the star here, and from that it predicts the other ones. And the fuzzy sphere, is limited to very small system sizes. So there's some question on how do you extrapolate it and so on. And I think we doing QMC, we have the least issues like that. We have big systems, no approximations, and so on. But still, still it's not easy, right? I would be happy to discuss more later. Okay, so what we are doing is again quantum Monte Carlo, but now for these dynamic quantities, we actually need to do analytic continuation because we can only compute time dependence in imaginary time, and then the analytic continuation to real frequency is quite challenging. But we have some progress there in terms of methods that allow us to do things a little bit better than before. And you can look at Sabine Young's poster, which will be up tomorrow, I guess, where he at least a little bit talks about the methods that we use. Okay, so already a few years ago, we looked at the dynamic spin structure factor. In that case, we did a spin anisotropic model for reasons that I will not get into here. And with Seong Meng, whose student Nissen Ma did the simulations, we collaborated with people doing field theory, and we computed this dynamic structure factor. So let me show you what we see. So here you see a cut through the Brillouin zone, and you see this color coding. You can imagine the brighter color means higher intensity. And then these dashed lines are actually from theory, basically from a fractionalized theory, a Parton theory, which is then subject to mean field treatment so that you actually can do something. And there are actually many candidate field theories that are supposedly related by this web of dualities here. And in principle, they should all be the same, but at the mean field level, they are not the same. And then the question is, what theory works best at the mean field level? And what was found is that if we look at this lower bound here, it actually has exactly the form expected in a very simple mean field theory of this NF equals 4 compact QD3, namely the pi flux state on the square lattice. So that looks pretty good. So in the theory, even including some RPA corrections and so on, one can get a similar continuum of excitations that looks pretty similar to this one. So it does look like we can see spin on deconfinement because this is the spectrum of two deconfined spin-ons. Okay, so that was for the spin anisotropic model. Now this is Sabine's result for our spin isotropic model. And also here you may see that our lower edge is sharper here, and that's because our analytic continuation now sort of builds in a sharp edge. We don't need to know where the edge is, but just that there is an edge. So there's less of this or none at all rounding of the edge here. And again, the only adjustable parameter is an overall amplitude here. And again, if you look at Sabin's poster, you will find some tests on actually 1D models where we can make sure that these methods work well. Okay, now let's look at the single hole dynamics. So now, what I told you about so far was in purely spin models, right? But now when we inject the hole, then the fermionic nature of these spins or particles becomes manifest. So then we need a kinetic energy for our hole, and that's just given by the standard TJ model T term. So we just add the T term to our JQ model. So here's an illustration that's been made for the 1D case. So we have our spin chain in this case, but what I'm going to talk about is 2D. And then, a hole is put in here, and then, the hole can move, and that actually causes sort of a domain wall. So two upspin in this case adjacent to each other. And then the hole and this domain wall, which is now the spin-on, they can move independently of each other, more or less. And that would be what we call spin charge separation or deconfinement. So what we want to see now is if something like that happens in the 2D system. So as a little test here, first I show some results for the standard TJ model, which has this so-called supersymmetric point where T over J is 1/2, where there's actually some exact results that we can compare with. So here is the spectral function, and in this case, we believe that there is actually a quasi-particle, so there's no spin charge separation in the TJ model itself. So then we do the analytic continuation under the condition that there is actually a delta function at the lowest edge of the spectrum. And here we see the quasi-particle weight as a function of the momentum. And you can see here that there's a special point here, 0, 0, where you don't quite see it, but there's only a delta function there. So at this supersymmetric point at momentum k equals 0, one can actually solve exactly for A of Q and omega, and it's a single delta function at omega equals 4. And that's exactly what we get. We get the one for the quasi-particle weight. And you can also see that the dispersion minimum is at pi over 2, which people have known for a long time. And also there's an interesting thing here. If you look close to pi 0, it looks pretty flat, especially if you go in some direction that is not really shown here. It's actually very close to a quartic dispersion. Previous calculations for the Hubbard model had not really seen the difference in energy between those 2 points, but in a recent work on the Hubbard model together with Shewei Zhang and my student Gabe Schum, we actually also saw this difference in energy between these points. And the fact that the band is almost flat here actually leads to a very interesting shape of the density of states in the 2D Hubbard model. So if you're interested, you can look up that paper. Okay, so now let's look at what is the main thing that we wanted to investigate here. What happens if we inject the hole at this deconfined critical point? So then again, we believe that we have no sharp quasi-particles. So again, we impose the edge in our analytic continuation. So here you can see some examples of the profiles at some given momenta and as a function of omega. And this is basically what we get in this color coding here. So again, we see a continuum, and there's some features in this continuum that it's not actually quite clear to us as what they are. But then we can say, well, if we have complete spin charge separation, then we should again have independently propagating spin on and hole on. So that means that from that, the lower edge that we see here should be the lowest combination of spin on and hole on energies you can get with a given total momentum. So the spin on plus hole on energy is the sum of the spin on and hole on, but you can have many different such combinations. But now we can find the minimum. So if we know the spin on energy and the hole on energy, we could find the minimum here. But we don't know the hole on, but we know the lowest edge of the combination, right? So that actually allows us to solve for the hole on energy, because we also know the spin on energy. That's what I showed you already before. So that's the blue curve here. And our total, that means the edge that I showed you for the spin on and hole on, that's the red one. So what we find is that the hole on energy is this black curve here. But now there's a problem here, because if our assumption is okay, namely that the spin on and hole on propagate independently, then we can take our results for the spin on and hole on, and then we can go in the other way and extract what is the minimum edge when we have two of them. And that turns out it's the same as the hole on band here. You can think of that as you take this hole on energy and you can add a spin on which has zero energy at momentum zero. So then you would get the same one, and that turns out to be the minimum. So that actually means this mismatch here then must mean that that our assumption is violated. There's actually not complete deconfinement, but instead there is some kind of interaction between the spin on and hole on. And it should be an attractive interaction. So within the deconfined criticality theory, there's a natural candidate because there's a gauge field there. So probably these coupled to the gauge field, and that somehow gives them some attraction. But nevertheless, it's they're probably close to deconfined because we do see a pretty prominent continuum here. Although in principle, it could be that we have actually a quasi-particle at the lower edge, and this is just some multi-particle continuum. Okay, but there has also been analytical work on related issues by Ribucal and co-workers. So what they pointed out within a field theory approach is that if you dope a system at the deconfined critical point, then you should get what they call a hole-on metal, which is basically a metallic state where the hole-ons and spin-ons are deconfined. So they discussed the properties of this hole-on metal, but they did not include any sort of attraction between the spin-on and hole-on. So maybe it would be good to try to do more work here theoretically as well. Okay, let me talk about one more thing. I don't know how much time do I have left. Okay, good. So we can still also look at the spectral function in the VBS phase. So here is one example of that, sort of moderately deep into the VBS phase. I didn't put the actual numbers here. So again, you see that we have, well, in this case, we actually do expect from, very simple argumentation, we expect a spin on hole on bound state, also called a spin polaron, which is slightly misspelled here. So this is the quasi-particle weight we find for that. And then you see that there's also some continuum there. Now, Ribukal et al. Also within their hollow metal paper, they also discussed what should happen if you dope the valence bond solid state. And in fact, you should get some sort of Fermi liquid with these Fermi pockets. Well, so that's in the Nel state. This is well accepted now. I think that you get these Fermi pockets if you dope, for example, lightly dope the high TC cuprates. But if you do the same in a VBS, these pockets will shift. So in this case, they have in the figure they have shifted them in towards the center of the Brillouin zone, but they could also shift out. They could not really say what is the sign and magnitude of this shift. But we can look at this with our methods, and this is what we get. And so this is a color coding of the whole Brillouin zone, and it's the energy relative to the ground state. So black would be the lowest energy. All those have been put red dots at the very lowest points, just so that you can see them more clearly. And this is a little bit inside the VBS, and this is further inside the VBS, and you can see that these minimas have actually shifted in the way they proposed, although in this figure they show them shifted in. What we find is that they are actually shifted out. Okay, so I think I'm pretty much out of time, but let me just mention an experimental paper on strontium copper borate, which I think at the moment is the best candidate material for deconfined criticality. So in this experiment, which was done at Renmin University in Beijing, when I also was visiting in Beijing at the time. So they did high pressure, low temperature, and pretty high magnetic field experiments, NMR. And I just show one figure from the paper here that you can see if you go to quite a high pressure, 2.1 gigapascal, you can see that there's actually a transition in what's called a plaquette singlet state, which is another singlet pattern state similar to the valence bond solid, but the singlets form on 4 spin plaquettes instead. And then as a function of magnetic field, you can see that the TC of that phase goes down, and at some field you instead get an antiferromagnetic phase. And if we blow up this part here a little bit and also include data for 2.5 GPa, you can see that they actually, these transitions come together at a very low temperature, about 0.07 Kelvin. And actually it turns out that it's a weak first order transition. Such a low temperature of where these come together, considering that they start at T around 2 Kelvin and maybe 1 Kelvin, and they go down quite a lot in temperature. That's a bit unusual. And furthermore, one can actually see scaling behavior of, in this case, what's plotted here is the spin lattice relaxation rate with some shifting of data and so on. You can actually, in principle, read off an exponent here, which actually is in pretty good agreement with numerics for these models that I've been talking about. Okay, so for more details, you can look at the paper. Let me just conclude and say that deconfined criticality is still not fully understood, right? But with these JQ models and by using large-scale numerics, we can get reliable numerical results. And I hope I convinced you that we can get quite a lot of spectral details now. And maybe the main result we have here is that it appears that there's not complete spin charge separation. Whereas actually the spin on deconfinement seems pretty much complete because we agree with this, deconfined, lower bound and everything. Okay, so that's it. Thank you.
And I have a couple of questions.